Hi, today we will discuss the method of joints in analyzing the 2D truss. As an overview, we have the motivation, the background of the method, procedure for analysis, some examples, and the set of force members. Here is a space truss that was designed in Berlin Central Station. As you can see, the blue portion is in tension and the red no in compression, and the red one in tension. And also it was specifically designated that there will be hinges in between. Of course, they were able to analyze that one accordingly. As you can see, there are two types of trusses: the Berlin Central Station and almost the same with the Waterloo Station. As a background, if a truss is in equilibrium, then each of its joints must also be in equilibrium. Hence, the method of joints consists of satisfying the equilibrium conditions, that is summation forces x is equal to 0 and summation forces y is equal to 0 for the forces exerted on the pin at its joint of the truss. When using the method of joints, it is necessary to draw its joints free-body diagram before applying the equilibrium equations. Recall that the line of action of its member force acting on the joint is specified from the geometry of the truss, since the force in a member passes along the axis of the member. As an example, consider point or joint B of the truss below. From the free-body diagram, the only unknowns are the magnitudes of the forces in members BE and BC. Normally, as in notation, if we are referring to the joint, in the notations we normally use the joint number first, then the other joint. So we have BE and BC. As you can see, the force FBE, that is the force in the member B, is pulling on the pin, which indicates that member BE is in tension. Whereas FBC, that is the force at member BC, is pushing on the pin, and consequently member BC is in compression. Here you will notice I am actually using the blue color for tension and red color for compression, and you can consider that one, or you can use that one to remember that we are talking about tension and compression. Anyway, it's just a notation. You can always use any other colors in your choice. These effects are clearly demonstrated by drawing the free-body diagrams of the connected members. So as you can see, we have separated the two free-body diagrams of the connected members, which is both in tension and compression. So you can see the free-body diagram at joint B is shown here. In all cases, the joint analysis should start at the joint, remember, having at least one force, and at most two unknown forces. At most, so that's the maximum. It should be two unknown forces. Otherwise, you cannot solve it. In this way, application of the summation forces x is equal to 0 and summation forces y is equal to 0 yields two algebraic equations that can be solved for the two unknowns. So normally, when applying these equations, the correct sense of an unknown member force can be determined using one of the two possible methods. By the way, I just want to emphasize here the two equations of equilibrium. It says along x and y axis. It's not necessary. You can also say summation forces horizontal is equal to 0 and summation forces vertical is equal to 0, or depending on the orientation of the local axis. So here are the two methods in determining the correct sense of the unknown forces. The first method is that always assume the unknown member force is acting on the joint's pre-body diagram to be in tension, that is pulling on the pin. This will yield positive scalars for tensions or for members in tension, and negative scalars for members in compression. Because when you are solving, uh, if the result is negative, then it means compression. And if the result is positive, it means you are right in your assumption that it is in tension. So once the unknown member force is found, use its correct magnitude and sense, either tension or compression, on subsequent joint pre-body diagrams. This is the first method. And if you are really not familiar, you can just use directly. But I suggest you have to use method 2, because this is quite intuitive, and this is what I am talking about, that we have to learn, we have to understand the behavior of the structure. And if you are used to it, you will easily know if it is in tension or compression. So in the method 2, the correct sense of direction of a non-member force can, in many cases, can be determined by inspection. So just by using inspection, you will know if it is in tension or compression. Anyway, don't worry. Uh, you will develop that skill along the way as we go on with our discussions. For example, the force FBC must be must push on the pin compression, since its horizontal component FBC sine 45 degrees must balance the horizontal force 500 Newton. Uh, Likewise, FBE is intensile force, since it balances the vertical component of FBC, that is FBC cosine 45, which is going up. So in more complicated cases, the sense of an unknown member force can be assumed. Finding compression or tension by inspection. Here is the key to imagine its member. That is, imagine its member in turn to be cut or removed from the structure while under load. This will produce, of course, an unstable structure or mechanism. Okay. If the nodes at its end of the member would move closer together and hence have to be pushed apart to prevent collapse, then the member is in compression. This is shown on the diagram by placing a small arrow close to the end of the member as follows. That is pushing the nodes apart. Again, this is just a notation. You can use your own notation, which is the opposite of this one. For purposes of discussion, we are using this notation for compression. Conversely, if the nodes at its end of the member would move apart and hence have to be pulled together to prevent collapse, then the member is in tension. This is indicated as the arrow sign, that is pulling the nodes together. This is best illustrated by considering an example. So here, in most cases, it is easy to determine whether a truss member is in tension or compression simply by looking at the structure. This is an important skill that should be developed, as it can expose embarrassing fundamental errors in numerical calculations. For example, below is a cantilever bracket for supporting pipes. So you will see with different dimensions. By simply looking at the structure beginning from the right end, joint E, we can easily see that the forces in its member are shown, that is blue in tension and red in compression. In any analysis, it is easier to proceed if we can draw the structural model as shown on the right. The weight P of the pipes are drawn vertically downward. Remember, the weight is due to the acceleration of gravity, which is directed vertically downward. Here is the procedure. Cut mentally its member in turn and to picture how the structure would be formed. Of course, I was able to find this picture from Seaward. It's quite interesting actually, because it's a nice diagram that represents the the bracket. If we cut the member AC, what will happen to the person? Can you imagine? There are forces here on this side, and then there is this person. So force C or joint C tries to move away from point A. So member AC must pull, or this is in tension. That's how we we know that EC is in tension. Another one is member CE. Again, cut the member CE with the effect of the external load. What will happen to the person? Uh, the person will be in tension. Okay. Another is in member BD. If we remove or cut the member BD, what will happen to the structure? Of course, there are two forces here on the right, so the thrust will move downward, which is going near the joint B. So point D or joint D tries to move towards joint D. So the member BD must push, that is in compression. Also, if we have to cut or remove member DE, what will happen? Uh, Again, the member DE will be pushed, so this is in compression. And also, when we remove uh, member BC, this is more difficult actually than the first three or first four members, because this is an internal member. When BC is removed, the rectangular ACB or ACDB wants to form into parallelogram. So it will deform like a parallelogram, something like that. So joint C is moving towards or closer to B. And since joint C is moving towards B, then BC must therefore push to prevent this. So hence it is compression. And last member is that D tries to drop away from C. So CD must pull, that is in tension. So as a summary, here is the representation of the members in tension and compression. So as you can see, member AC is compression, member CE is compression. So with member no, sorry for that. It's in tension. Member AC is tension. Member CE is tension. And member CD is in tension. The rest, CB, DB, and D are in compression. So what is the procedure for analysis in using the method of joints? Here are 5 steps. First, you have to draw the pre-body diagram of a joint, having at least one known force and at most two unknown forces. If this joint is at one of the supports, it may be necessary to calculate the external reactions at the supports by drawing a pre-body diagram of the entire structure. Normally, when we are analyzing a truss, we normally compute first the reactions and then the member forces. Step 2. Use one of the two methods previously described for establishing the sense of an unknown force. Step 3. The x and y axis should be oriented such that the forces on the pre-body diagram can be easily resolved into their x and y components. Apply the two force equilibrium equations, that is summation forces x is equal to 0 and summation forces y is equal to 0. There should be summation here. Solve for the two unknown member forces and verify their correct directional sense. Step 4. Continue to analyze edges of the other joints, where again it is necessary to choose a joint having at most two unknowns and at least one force, one known force. And last step, once the force in a member is found from the analysis of a joint at one of its ends, the result can be used to analyze the forces acting on the joint at its other end. Remember, a member in compression pushes on the joint and a member in tension pulls on the joint. Here is an example the bracket that we are talking earlier, of course, every 5 meters, and the total design load of the pipes is 3.8 kilonewton per meter. Determine the value of the forces in all the members by hand calculation and by skill drawing. Skill drawing can be will be discussed in separate lecture. Ignore the self-weight of the truss, and the use of the term design load above implies that any load factors for loads have already been applied to the service loads. So either you will be using allowable strength design or strength design method, or the LRFD. So here it is first necessary to determine the design load on one bracket. Since the brackets are, as you can see, uh, are there for every 5 meter length of the pipe. So there is one bracket. So the tributary width is 5 meters. So the weight of pipes supported by each bracket should be 5 meters times 3.8 kilonewton per meter. That is 19 kilonewton. Because of symmetry of pipes, we can divide this weight equally between nodes D and E. So therefore, the load per joint is 19 over 2, or 9.5 kilonewton. If we allow for a self-weight of the truss load per joint, then we can say that the P is 10 kilonewton. So we have this structural model below, uh, the structure above, and we have drawn the structural model using the stick model, and we have some circles at the joints to represent that we are the members are connected in a pin connection. So here is the method of joints. We will look first for the joint the with at least one known force. It's either D or E, and then at most two unknown forces. At most, that's the maximum. At joint D, we have 1, 2, 3 members with unknown forces, so do not use D. But at point E, we have 1, 2, D, E, D, and EC. We have two unknown forces here, so the candidate is joint E. So the two unknown forces FEC and FED must be in equilibrium with the applied load of 10 kilonewton. In other words, the vertical component of all the forces must sum to zero, and likewise with horizontal component. Here, uh, the force FEC, we assume that this is in tension because the vertical component of this will be in equilibrium with the force 10 kilonewton, which is moving downward. And same with the FED, it is in compression because the horizontal component of FEC should be in equilibrium with FED. So the above FEC is tension, FED is compression. Here we will be using, instead of the angle, we will be using the slope in terms of 1 vertical, 1.5 horizontal, and the hypotenuse is square root of 3.25, which is computed using Pythagorean theorem. That is the square root of one side square plus the other side square. That's square root of 3.25. So here we will apply the two equilibrium equations, and it's easier if we compute first the vertical forces because there is only one unknown. Of course, you can always use summation forces x and then y, but there will be two unknowns in two equations, and again, most likely you will commit errors if you will do that. But you will look for uh, possible equations that has only one unknown. So in this case, we will use summation forces y is equal to 0, assuming vertical forces are going up as positive. So the component of FEC is equal to the vertical slope 1 over the square root of 3.25 times FEC, or that's FEC times sine theta, minus the vertical force of 10, which is going down. So here you can compute for the force of FEC, that's 18.03 kilonewton, and since the result is positive, then we are right with our assumption that it is in tension. Next is summation forces along x is equal to 0, assuming to the right as positive. So we have FED minus the horizontal component of the force FEC, that is FEC times cosine theta. Here cosine theta using the slope, we have 1.5 is to the square root of 3.25. And since we have computed FEC above, that's 18.03 kilonewton in tension, you can just substitute it into this equation to solve for FED, that's 15.0 kilonewton, which is compression. So we are correct with our assumption, and then after that we can proceed to joint D, since one of the member forces is already known, and we have one force or one external force, and we have two unknown forces. So here this is quite simple because we have only vertical and horizontal forces. So you can just use summation forces x is equal to 0. So FDB is equal to FDE, where FDB is equal to 15.0 kilonewton, which is also in compression. If you sum up forces vertical, or summation forces y is equal to 0, showing upward direction as positive, then FDC minus 10 is equal to 0, solving for FDC. FDC is 10 kilonewton tension. The next we can go up because joint C has two known forces already with two unknown force. So here again we use the slopes to determine the horizontal and vertical components of the force FCB and FCE. And we know that FCE is 18.03 kilonewton in the previous computation, and also FCD is 10 kilonewton, which is in tension, both in tension. So since both of them are in tension, uh, the the member FCB, or the force in member FCB should be upward, or its vertical component should uh, be in equilibrium with these two tension forces. So that's why FCB is assumed to be compression. And if you take the horizontal components, the FCE will be in equilibrium with the horizontal component of FCB and FCE. So that's why it is assumed to be in tension. So here again we use summation forces vertical because FCE has no vertical component, so only FCB. So we only have one unknown. So FCB times the vertical slope 1 over square root of 2.44, then minus FCD, which is vertical, then minus the vertical component of FCE times 1 over square root of 3.25. Substituting the values of this, we can solve for FCB, which is equal to 31.24 kilonewton in compression. Also, we can now use the summation forces horizontal, which is equal to 0. So we have minus FCE plus FCB times the slope 1.2 square root of 2.44 plus FCE times the slope 1.5 over square root of 3.25. Solving for FCE, that's 39.0 kilonewton in tension. So far, the values of all member forces have now been found. However, a designer would also need to consider the connections to the wall at support A and support B. Hence, values for the reactions are required. Because only a single member is connected to joint A, the reaction at A must be in line with the member and of equal and opposite value. Hence, RA is equal to 39.0 kilonewton, which is equal to FCE. For the reaction at B, we divided it into vertical and horizontal components. So we have RBH and RVB. So here, if we sum up forces vertical, we can solve for RBV. So that is 20.0 kilonewton, which is going up. And if we sum up forces along the x-axis, which is equal to 0, we can compute for RBH because we already computed are FBC and FBD. So here RBH is 39.0 kilonewton. These two components may now be converted to the resultant reaction force, and its angle of action can be calculated. So normally we took the resultant for the two reactions, the horizontal and vertical, using Pythagorean theorem. So the resultant R is square root of RBH square plus RVV square, which is 43.83 kilonewton, with the direction with respect to the horizontal, that is the arctangent of 20 over 39, which is equal to 27.15 degrees. And then for the overall equilibrium check, again, just like what we did in beams in computing or using the equilibrium equations, we check our results. So with this truss analysis, we need to check our result, because it is very easy to make numerical errors in calculating the forces in large trusses, but there is always enough information to make an independent check. In this case, it is possible to check the reaction forces by looking at the equilibrium of the whole structure. So we will just use the whole structure and check it using the equations of equilibrium. If we sum up moment at point B, assuming counterclockwise moment will be positive, and equate this to 0, so we have the external force 10, which will be clockwise, 10 times 1.2 plus the other 10 times 1.2 plus 1.5, that's 2.7, will equal to the reaction at joint A times the distance 1.0. So here RA is 39.0 kilonewton, which is going to the left. We assume that it is going to the right, but the result is going to the left. If we sum up forces horizontal now, or summation forces X is equal to 0, then we have minus RA, because we are assuming that this is going to the right, plus RBH is equal to 0. Or since we have computed, we have known that RA is going to the left, so we have minus RA plus RBH, which is equal to 0, where RBH is also equal to 39.0. Then lastly, summation forces Y is equal to 0. We have RVV minus 10 minus 10. So the result is RVV is 20 kilonewton, which is also correct. So we are done with analyzing the whole structure using the method of joints, and we also were able to check if our calculation is correct. So that's how we do the method of joints in analyzing a 2D truss. So we have this final result. I have drawn this earlier, but at least I included the forces or the quantities of the tension members and the compression members. Just to give you a small overview, this is a preliminary design using allowable stress design. We assume that the result is using the allowable strength design. So the tension member, as you remember, the Hooke's law is stress is equal to the force P over the cross-sectional area. If you find for A, the equation will become P over stress, where P is the computed force and the stress is the allowable stress, normally 60% of the yield strength of the steel. If we use steel for the tension member, which is the usual, Fy is usually 248 megapascal. So multiply it by 6 and take the reciprocal, multiply it with the computed value, the maximum tension force that we computed, 39,000 newton. So that the area that we needed is 262.1 millimeter square. You have different options. So we can use the round bar. So since this is an area, and you can compute for the minimum D. The minimum dimension of the round bar is, or diameter is 18.27 millimeter. We don't have 18.27 millimeter bar, so we can go directly to the standard, which is 20 millimeter diameter, or 3/4 of an inch in diameter. aside from that, you can also use plate or bar. It can be square or rectangular. So here we required a 1/4 millimeter thick plate, so it will give us 2 inches width, or 41.28 millimeter by 6.35 millimeter. But we don't use 41, so you can just use 45, or 2 inches, 50 mm, or 50.8 millimeter. This is 2 inches times 6.35 millimeter. Or you can use an angle bar. Angle bar is normally capital L. That's 51 mm by 51 by 3.2 mm, or 2 inches one side by 2 inches the other side, times the thickness of the angle bar. That's 1/8 of, and then the provided area for this angle bar is 370 millimeters square, which is more than enough for this particular problem. So actually, this is the essence of I am discussing with you. You should be able to know the or understand the behavior of the structure. You will be able to determine the forces, and then after the forces, the stress, the strain, and then you can design. So this is the overall uh, concept of structural engineering. Of course, there are more on designs. I just give you a preliminary design for a particular member. So we have here another example taken from HIBBELER. Determine the force in its member of the roof truss shown in the photo. The dimensions and loadings are also shown in the figure. State whether the members are in tension or compression. So as you can see, the external forces are vertical, which is applied at the joints, and the reaction forces, first for the hinge support, we have Ex is equal to 0 because there is no horizontal force applied, and the vertical force A sub y. Also the reaction at D, since it is roller, so we only have one reaction that is perpendicular to the surface, that is D sub y. Due to the symmetry of the loading and of the truss, we can just get half of the loading. So 3 plus 2 plus 3, that's 8, divided by 2, that's 4. So the reaction at A sub y is 4 kilonewton, and reaction at D sub y is 4 kilonewton. If you are not convinced, you can take moment at A to solve for dy, and then take moment at D to solve for ay, or sum up forces vertical, you will get the same results. Okay, so in this case, as I mentioned earlier, the loading is symmetrical. So with the truss formation, which is also symmetrical, so we can take advantage of that property, meaning the forces involved in the members on the left will be the same as the members on the right because it is symmetrical. So we will simply analyze half of it. So meaning joints A, G, B, and then F. Actually, by analyzing A, G, and B, you are done. You can just use joint F to check your work, because by analyzing point A, you will be solving a G and a B. Analyzing joint G, you will be solving G. No, G is given. You will be solving for GF and GB. And by analyzing at joint B, you will be solving BC and BF. So you are done. And use F to check your work. So here at joint A, we can start at joint A because there is only one uh, external force, and at least or at most two unknown forces, that is FEB and FEG. Here we can directly compute for FEG. We assume that it is compression because the vertical component of that will be in equilibrium with 4 kilonewton, which is going up. So FEG should, the vertical component should be going down. So it is in compression. And also the force in FEB should be in tension because that will equilibrate the horizontal component of FEG. So here you can apply summation forces y is equal to 0. We have 4 minus the component FEG, that is because it's opposite, so sine 30 degrees FEG. is equal to 0. So compute for FEG, which is 8 kilonewton, which is positive, so it is in compression, capital C. If you use summation forces X is equal to 0, we have FEB minus the horizontal component of FEG, that is cosine 30 degrees times 8, is equal to 0. So FEB is equal to 6.928 kilonewton, again in tension. At joint G, in this case, note how the orientation of the x and y axis to avoid simultaneous solutions of equations. So here, this is what I'm trying to see earlier, that you can orient the axis in a convenient direction. So here, we assume that the x-axis is this way, and perpendicular to that is the y-axis. But you have to be careful with the angles. Here, F is 60 degrees with respect to the x-axis, and uh, the FGB is 60 degrees with respect to x, or 30 degrees with respect to y-axis, or the 3 kilonewton is 30 degrees with respect to the y-axis. So if we have to sum up forces along the y-axis, we are only dealing with FGB. That's FGB times sine 60 degrees, or that's cosine 30 degrees, minus 3 times cosine 30 degrees, which is equal to 0. So FGB in this case is 3.0 kilonewton, which is in compression. Also, if you sum up forces along the x-axis and equate to 0, we have 8 minus 3 times the opposite, so the sine 30 degrees, minus 3 times cosine 60 degrees, minus FGF. The only unknown force is FGF, then equate to 0. So FGF is 5.0 kilonewton, which is in compression. And the last joint, we have joint B. So we have two unknowns remaining, FBC and FBF. FBF is in tension because the vertical component of 3 kilonewton should be in equilibrium with FB, the vertical component of FBF. And FBC is in tension because this should equilibrate the horizontal components of the force. So summation forces y is equal to 0. We have FBF times opposite side, so that's sine 60 degrees, minus 3 opposite also, so sine 30 degrees, then equate to 0. The FBF is equal to 1.73 kilonewton, which is in tension. You can also sum up forces along the x-axis, which is equal to 0. We have FBC plus 1.73 for FBF, cosine 60 degrees plus 3 cosine 30 degrees minus 6.928, which is equal to 0. The resulting FBC is positive 3.46 kilonewton, so our assumption is correct. You need to check your solution. You can use the equilibrium equation in joint F to check our solution. I will not show it here so you can try it yourself. So this is the final result. As you can see, since the forces are vertical and we have supports on the left and on the right, if you have forces vertical, it's the same as the paper. Yeah. If you apply force vertical downward, so the members at the bottom should be in tension, and the members on the top should be in compression. So as you can see, the top chords are compression and the bottom chords are tension, and the rest of the members will alternately be either tension or compression. So much for that. It would be much easier to analyze a truss if you can pinpoint directly by inspection the zero force member. What does it mean? Actually, there are forces that will not carry any. There are members possibly that will not carry any loading. The truss analysis is greatly simplified if one is able to first determine those members that support no loading. We call it the zero force members of a truss. which can generally be determined by inspection of the joints, and they occur in two cases. Case 1, the two members at joint C, in the example on the right, are connected together at a right angle. Take note, right angle, and there is no external load on the joint. So if you draw the free body diagram of the joint C, it indicates that the force in its member must be zero in order to maintain equilibrium, because there are no external forces at joint C. So FCD and FCB should be zero. So this member BC and CD are the zero force members. What else? Look at joint E. Uh, as this joint, this must be also true regardless of the angle theta. I mentioned earlier it should be 90 degrees and uh, no external load. And since there is no external load on A, and even though it's not a right triangle or not right angle, it does not really matter. Again, the member AB and EE is also a zero force member. You can check that one by drawing a free body diagram at joint E. Look at the right figure, and if you sum up forces vertical and horizontal, the two member forces are both zero. But take note, the zero force member are important. You might be thinking that you have to remove that one. The zero force members may be necessary for the stability of the truss during construction and to provide support if the applied loading is changed. So although it's a zero force member, it's very, very important. Do not remove it. The other case 2, is that the zero force member also occur at joints having a geometry as joint D. Look at the figure below. Here, no external loads acts on the joint, so that the force summation in the y direction, which is perpendicular to the two collinear members, requires that F dF should be equal to 0. So using this result, FC is also a zero force member as indicated by the force analysis at joint F. If only two nonlinear members form a truss joint and no external load or support reaction is applied to the joint, then the members must be zero force case member, that is case 1. If three members form a truss joint for which two of the members are collinear, remember, two of the members are collinear, the third member is a zero force member, provided no external force or support reaction is applied to the joint. This is case 2. So particular attention should be directed to these conditions of joint geometry and loading, since the analysis of a truss can be considerably simplified by first spotting the zero force members. So here is an example. You can use the method of joints and indicate all the members of the truss shown that have zero force. You can try it by yourself. You can pause first the video and try it by yourself. You can apply case 1 or case 2. Okay, I hope you have done your part. You have tried looking for the zero force member. Uh, we can start joints with no loading. At joint D, there is no loading. So even though it has an angle theta in between DE and DC, since there is no external load, these two members should be zero. Where else? Joint G. At joint G, there are two member forces, but there is no vertical external force. So member EG should be zero. What else? In joint H. At joint H, there is no external force, although the two members are collinear, but the other one, uh, BH, is this BH should be equal to 0. So we have pinpointed DC, DE, EG, and HB as the zero force member. Here are the details of that analysis. So if we try joint D, and if you try to sum up forces, it will give us zero forces for FDC and FD. So we are right at joint D. Also at joint E, going back here, this is joint E. Since we forgot this one because there is no force at DE, so there should be no force also in EF. And here, the force EF. And then joint H, two collinear members, but there is no external force, so its B should be 0. And lastly, joint G, there is horizontal force at G but no vertical force. So the force G is equal to 0. That's how we determine the zero force members of the truss. Knowing the zero force members, it would be easier for us to use the method of joints to calculate the member forces. That's all for the method of joints, and I hope you're able to understand how it is done. And again, the method is quite simple actually. You can use the equation of equilibrium. First, draw the free body diagram of every joint, especially the joints with one external load and at most two unknown forces. You really have to try by yourself. Okay, try solving it alone so that you will be able to understand fully the method of joints. That's all for today, and thank you for listening.